into what makes Kudu special. So, as I said, it's a fast columnar storage engine. And the use cases we're targeting are time series use cases where you're continuously ingesting data, and you need that data to be ingested with low latency and with high durability. So, for instance, for those of you that were present for Eric Semmer's Rocana talk, we do exactly one semantics. And we use consensus, so you can be assured that your data will survive, even if the whole data center comes down. The other thing that we target Kudu at is machine data analytics, right? So having Kudu be the target of your data, and at the same time be the source for your analytic pipeline, your SQL queries, your machine learning algorithms, etc. Finally, online reporting, right? So your inserts, updates, and scans and lookups for whatever reports you need to build online using SQL or something else. But usually for these, you traditionally use SQL. So what are the external user features of Kudu? It has a SQL-like schema, right, with a finite number of columns. It's columnar, so you know that your data is going to be stored in neat little columns that are going to be compressed and encoded so that they can be efficiently accessed, and I/O is very efficient there. You have all your familiar types, with the exception of decimal, which is not implemented yet. And a subset of those columns makes a possibly composite primary key. So you always have a primary key that cannot be duplicate because it's a primary key. And you have super fast alter table, which doesn't actually stop the cluster to change your schema. We have Java and C++ NoSQL style APIs. If you're familiar with HBase's API, you're going to be super familiar with Kudu's API. And we have integrations with Impala and Spark and MapReduce and more to come. Oh, sorry. So what do we aim to solve, right? So there's a couple points to it. One of them is, why did we build Kudu with the way we built it? And we built it the way we built it as an efficient C++ storage engine because a few years ago we got together and you thought the next bottleneck is going to be the CPU. I/O is getting faster and faster, network is getting faster and faster, and the next bottleneck is going to be the CPU. So Kudu was designed from the get-go to be very, very CPU efficient. And the other more user-facing use case that we aim to solve is that we saw this pattern all over the place, right? So people would ingest data into some storage engine, like HBase, but maybe also Cassandra or anything else. And then every once in a while, there was this job that would transform whatever data you had on HBase into neat Parquet files that are very efficient to query. And then you'd run your analytics on those Parquet files, which means that your pipeline is actually quite long, right? So your pipeline might be a day or at least a few hours, which means your data is not immediately available for querying. So how do we solve that with Kudu? We solve that with Kudu by doing direct ingest and querying from the same place, right? We do that by making sure that your reads do not completely overpower your writes. We do that by making sure that your reads are super efficient. So, for instance, your reads are lock-free, which means that whatever logs you're acquiring for your writes are not going to impact your reads. And the improvements are multiple, right? So you have one system to operate instead of multiple systems and complex pipelines. There's no cron or background processes. You can handle late arrivals or data corrections with ease. And new data, as I said, is immediately available for analytics. So how does Kudu data get laid out internally? You have tables, right? Your typical SQL table, and that gets horizontally partitioned into tablets. If you're familiar with HBase, these would be your H regions. And basically, it's a logical a logical section of your key space, depending on how you partitioned it. We'll talk about partitioning a bit in depth later. And each tablet has 3 to 5 replicas, which are replicated with Raft consensus, which means that you're sure that any crash won't impact your data. And if you need to recover from a full data center meltdown, your data will still be there. And you have tablet servers, which are the servers that host these logical tablets. And they store the data on local disks, so it doesn't use HDFS for anything. So this is how your data layout looks like. Each one of these things is a logical server. Servers host multiple tablets. Each tablet is hosted by multiple servers. And one of the servers is the leader. It's the one server that is actually able to accept writes into that tablet. If that server fails, a new leader gets elected, and this process is usually pretty fast. We're talking sub-second leader elections. So if on the case of crash, it's likely that you won't even notice it because it gets completely masked by the client if you're using C++ or Java client. So regarding tablet design, inserts get buffered into a memory store and dependent to a log. So the log latency is the only I/O on your critical path, right? And every once in a while, they get flushed to disk in the neat columnar layout that is very similar to Apache Parquet. Actually, we created a lot of code from Apache Parquet. And updates use MVCC. MVCC is multi-version concurrency control. And what it allows you to do is it allows you to answer queries, consistent queries at runtime while data is being inserted. So that you know that if a write is actually mutating data, but it hasn't completed yet, that data won't be visible for read queries. It also allows you to do something interesting, which is to run select as of timestamp, which means that each individual write, each individual data item gets tagged with a timestamp. That is a mix of logical and physical time. And because it is a mix of logical and physical time, what this allows you to do is it allows you to query data items at any point in time and obtain a totally consistent view of the whole database. So if you do a scan as of yesterday, right? If you set the timestamp on the scanner to be as of yesterday, you get the database as it was as of yesterday with no causality inconsistencies. So, of course, this is available, but it's not the optimal path. The optimal path is to read whatever is there. That's what's fast. So if fast is what you want, that's available too. And there's no per row branches, or there's super fast vectorized decoding and predicate evaluation. And that's the key portion of the integration with Impala, right? Predicate push down and making sure that you read the least amount of data possible from disk. And performance worsens, this is a caveat that should be mentioned, performance worsens based on number of recent updates. So Kudu is targeted at insert mostly, update some workloads, not workloads where you update the same row a lot of times. So let's do a little bit of intro into Impala. Impala is a fast SQL engine, completely written in C++, works with a bunch of storage engines. And the architecture of Impala with Kudu works is something akin to this. So what you see there is that on the yellow squares are the Impala services, on the blue squares are the Kudu services. So Impala has 3 main important services, which is the query planner that actually gets the request from the user and decides how it's gonna execute the query. It has the query coordinator that is in charge of making sure that all the executors work in unison to actually produce the results you want. And finally, you have a bunch of query executors that actually do the work. So for any one query, it would go through the one query planner, one query coordinator, and a bunch of query executors. So, but you can target queries at multiple nodes, which is why each node has one. So the daemon process in Impala D runs on every node with data, so it's localized with the data. Each node handles user requests, as I just mentioned. You should use a load balancer to distribute the load across nodes if you're running a multi-tenant environment. And you have metadata management as the catalog service and system state repository, which means these are stats and stuff that can be rebuilt, but that you don't want to do all the time, right? So, but when it's kind of strange to call the state store stateless, but that's what it means, right? That you can rebuild the state of the state store if the whole cluster goes down. So, query execution phases are, if you're familiar with MPP databases, are pretty normal. So, client requests arrive via ODBC, JDBC. The query planner turns the request into a collection of plan fragments, and coordinator initiates execution on remote Impala executors. During execution, intermediate results are streamed between query executors using an exchange, and query results are streamed back to the client. So, how does query planning look like? For this query, which has two joins and a group by and an aggregation, what you do is that basically you have a bunch of scanners scanning from different tables, and we'll see how this applies to Kudu in a bit. So you have a single node plan, which creates a tree of plan operators, and then you partition that single node plan across multiple fragments, and the executors execute them, and you have cost-based join optimization and cost-based join distribution optimization, which means is that your joins get distributed according to the layout of your data. So a little bit more about the execution engine. It's written in C++, minimal cycle and memory overhead. Executing single queries does not take over the whole cluster. You can actually execute multiple queries, even if they are I/O or processing heavy at the same time. And it's focused on speed and efficiency. I'm going to speed up a little bit, otherwise I won't get to the juicy part. So how do they work together, right? So if you're familiar with MPP databases, this is going to sound familiar to you. The first step, you do the planning of the query, right? You query the state store to see the distribution of the data. You query the catalog service to know where the data is. You query the Hive meta store to know which tables there are. And you query the Kudu master. And the Kudu master returns to you an opaque distribution of the data all across the cluster. And why it's important that it's opaque, it's important because as we want to develop Kudu without having to develop Impala in lockstep, right? So what you do is that the planner phase of Impala asks Kudu for the for what's the best way to get this data, where are the best places to get this data from, and once that's done, it forwards the information about the partitions to the backend as is, without actually having to understand what's inside. And so what does a plan of Kudu plus Impala look like? It looks like something akin to this, right? So if this is a very simple query, select count from Kudu table. You have an aggregation, you have a pre-aggregation, and you have Kudu scan nodes that actually scan the Kudu tables. One thing that is missing here is the part of the predicate pushdown that happens before the query starts. So coming back to the query you saw before, this is how the query would look like running on Kudu and HDFS, where you're joining an HDFS Parquet table with a Kudu table, where most of the data is in Kudu. So the red portions are the portions that are running co-located with the Kudu nodes, and the blue portion is the portion that is coming from HDFS. So the step 2 of query execution is to actually distribute the query from the query coordinator across the query executors. And step 3 is about predicate pushdown. These are the scan tokens that I was mentioning before, the information about the partitions and what can be done, right? That was calculated at planning time, and are pushing that all the way down to Kudu. It turns out that we're actually a little bit more efficient at doing this than even Impala on Parquet is. So for memory resident data, we're actually slightly faster because of that, because of better predicate pushdown. Finally, what you have is you have the normal, you push down your predicates, now you start scanning the data, it's getting pulled up. Hopefully, the biggest portion of the data is going to come in into the local nodes, but some of it might have to be distributed. So you do pre-aggregation and you do all of those things that you can do before to try and trim the data before you send it across the network. And finally, you return the results to the user. So let's talk a little bit about partitioning. Partitioning is super important in this case, right? Defining your partitions. Your partitions define how your data is distributed, and you get one Impala scanner per Kudu partition, which is a tablet. So deciding on how you're going to partition your data across your node might be the difference between it being super fast and being awfully slow. So let's look at the DVL statement. You're familiar with SQL, you're familiar with this. You have create table, you name a bunch of columns, and then you have this distribute by clause that basically indicates how partitioning is going to happen. Right? In this case, this is the very familiar HBase-like partitioning. You're partitioning key space by range by defining a bunch of split rows that basically define your partitions. In between each split row fits a partition. Each one of those gets transformed into a tablet and is served by a tablet server. And below that, you have the table properties that you must specify for Kudu specifically. So you need to say what the storage handler is so that it knows that it's a Kudu table. You need to say the table name. It might not be the same as the Impala table's name. And you need to name the address of the masters so that it knows where to query the metadata. And finally, you need to say what the key columns are. Because otherwise, there's no way to specify. I mean, eventually you have primary key syntax for when you actually specify the columns, but right now we don't. So that's the way we specify the primary keys. So I'm gonna talk a little bit about partitioning because, again, it's super important. As I mentioned before, you can partition by range and just specify a bunch of split rows, and data is fully ordered across tablets. It splits the key space into multiple ranges, and which is one nice part of it is that if you do a medium to small scan, you're very likely to hit a single tablet, and your data will come back in order. So you can rely on that and not have to sort if sorting is required. But sometimes it's hard to know good ranges a priori, and write patterns may favor a small number of tablets. So if you have a time series workload, you've used range partitioning, it's very likely that you're always writing to one tablet, right? Which is not good because you're basically overloading that tablet with all your writes. So what can you do about it? Again, very common strategy, you can hash partition it, right? Splits the key space into multiple hash buckets, one per Kudu tablet, and that is not ordered across tablets. So if ordering is required, you need to do the ordering yourself, and you don't have to know the distribution of the key space a priori. The good part is writes get evenly distributed across the cluster, so all your cluster is accepting your writes. However, counterpoint, small to medium range scans now may hit multiple and will hit multiple tablets, right? So you might have to scan from the whole cluster. And data is not ordered across tablets, so you might need to order the data yourself. So we implemented something that is in between, which is a very almost arbitrary combinations of range and hash partitioning, which means that you can split it into range and hash it, or hash it first and then split it into range, depending on what columns you select to do it. And what this gives you is that it gives you the nicety of distributing your writes across multiple nodes, but still knowing that if you're scanning, you're not going to hit the whole cluster, right? So how do we ingest data? How do we ingest data into Kudu using Impala? So you can do it at table creation time. Super easy. Create table. Mention the properties we just discussed. There should be a distribute by clause in there, which I omitted. And you do select from whatever table you want, right? if you do this from an HDFS table and they're actually running a Kudu cluster co-located with your HDFS cluster, this will mean that very likely, if you chose your partitions right, the data will stay in the same node. So create table as select is one way to do it. Another way to do it after the table is created is to insert into your Kudu table by selecting star from HDFS table. Star or whatever you want it to be, of course. So what are the caveats? We are a young project. Kudu is a young project. Impala not so much, but the Kudu integration is definitely young, right? So what are the caveats? So continuous ingest, even though Kudu is designed for continuous ingest should not use Impala, which means that you should not be inserting single rows using Impala, right? This is why is this like this? Because Impala was designed for massive analytical queries. So if you try and insert a single row into Kudu, the planning will totally dominate insertion. So you might have insertion times into Kudu that average 2.5 milliseconds, 3 milliseconds, and your insert of a single row will take 100 because that's the time that Impala takes to plan the query. Which usually is not a problem because your queries are going to take seconds anyway and are going to process gigabytes, which for a single row is problematic. And so you should use Kudu's Java or C++ API for small inserts and updates or deletes. Another caveat is that this is ongoing, but Impala does not specify support specifying compression and encodings on creatively yet. What this means is that even though Kudu has the neat columnar files and supports compression and encoding, you still can specify that at table creation time. So you should use the Java or C++ APIs to create a table and then just do insert into select from. Finally, batch inserts from Impala. I mean, if you're doing an insert into select from, these are not atomic for now. So they may fail because if you're so Parquet doesn't require keys to be unique. So it might be that you're inserting into a Kudu table and then mid-query you find out, oh, there are duplicated rows. So what can you do that? It's not like the whole query will abort. No, part of your data might be there. One way to get around it is to use the ignore keyword, and it's supported in most insert, update, and DDL cases and delete cases, and allows you to basically ignore these failures. So what's on the roadmap? So one of the things that we still have to do is use the scan tokens that I was mentioning before to basically totally avoid sending starting scanners in certain nodes. Right now, they don't read anything, but you still have to start them. So the next step, this is again almost out, will avoid, if you're just querying a small portion of the key space, this will totally avoid actually starting scanners in nodes that you're not pulling data from. And the other thing that we're working on is Bloom filter pushdown. So Impala just got this major revamp. They're using Bloom filter drawings all over the place. Kudu has Bloom filters, so we're working on a way to basically pull those Bloom filters from Kudu storage and use them as they are on Impala. So user features, and these are on the Impala side. These are features about the Impala integration, not about Kudu or Impala itself. The Impala Kudu integration is still missing timestamp and decimal. Timestamp exists in Kudu, exists in Impala, but the integration is not done yet. And decimal does not exist in Kudu, even though it exists in Impala. Kudu supports merge and upsert, which we're bringing to Impala 2. Again, as I mentioned before, the encoding and compression selection on Impala DVL, and the selectors of timestamp syntax. You already can do it using the client, you still can do it using Impala, and you'll be able to do it soon using that syntax exactly like that. Another thing that we're just about to push that I'm working on it myself actually, is exactly once writes, which means that even though if you have the case where you if Impala is completely overloading the Kudu cluster and the Kudu node crashes, the writes will still survive and the query will move on as expected. So what's on the long-term roadmap? On the long term, we have a bunch of performance optimizations that we still have to do. We feel like there's a bunch of access to get there still. Shared memory, use Apache Arrow in memory format, skew-based partitioning, and cache query plans to decrease latency, even for single row writes, and ACID multi-row writes. This is something that Kudu was designed for, but it's not available in Impala yet. So let's go through benchmarks real quick. Here we have a TPCH Analytics benchmark with 75 tablet servers. And the scale factor is not so big. It's 100 gigabytes. So all the data is resident in memory. You have one of the queries from the TPCH benchmark, and we were kind of surprised by this because we were expecting to be a little bit slower than Parquet. And we're actually faster, at least for in-memory resident data, because we're efficient with predicate pushdown. So, what about? So in average, we're 35% faster than Parquet in this workload. So what about NoSQL random access? So this is comparing just Kudu to HBase, and it's interesting that for most workloads. So if you have a uniform workload, you're spreading your work across the key space, it's going to be closely matching HBase. If you have your Zipfian workload, though, if you're having a lot of a very small number of rows getting most of your updates, then Kudu is going to get slower because of what I mentioned before. It's not geared to have a lot of updates to the same rows. So production. So probably the biggest deployment of Kudu is at Xiaomi now. The last time I've heard, they had 200-something nodes running Kudu. I think they've upgraded since then. They also run Impala, which is why it's interesting here. So they report very high write throughput, and they can query the latest data with a quick response, and they can search for individual records. They actually contributed a very optimized path for single row fetch. And again, the reports that the results that they report are enthusiastic, right? So Kudu again beats Parquet in some cases, like query 6, by a whole lot. Again, this is the case. This is because of predicate pushdown. All right, right on time. So you can find more about Kudu at kudu.apache.org or follow Apache Kudu on Twitter. And you can find more about Impala on impala.io or follow Write Impala on Twitter. And I'm open for questions.
Yes, any questions? Okay.
Alrighty.
Thank you so much, David. It was a nice
Pleasure.
talk. Thank you so much. Once again, we have an announcement that we have a reception at 6:30 near Library Building. So be there. Thank you so much.